Something strange is happening with a visitor from beyond our solar system. Scientists keep revising their numbers upward, and what started as estimates of a few hundred meters has ballooned to something far more massive. This interstellar comet, named 3I Atlas, keeps surprising astronomers every time they point their telescopes at it. The measurements show it could be up to 7 miles across, making it the largest object from another star system we've ever detected passing through our cosmic neighborhood. Discovery in Chile. On July 1st, 2025, a telescope in Chile caught something moving through space at incredible speed. The Atlas system, designed to spot asteroids that might threaten Earth, picked up a faint dot near the border between Serpens Cauda and Sagittarius. Initial readings showed it traveling at 61 kilometers per second. That's fast enough to cross the entire United States in less than a minute. Within hours, astronomers realized this object wasn't following the usual rules. Its trajectory showed the telltale signs of something that came from outside our solar system. Confirmation and designation. The Discovery team ran through their confirmation checklist. They pulled up older images from NASA's TESS spacecraft, finding the same object captured back in May. Those early photos from May 7th to June 3rd revealed activity happening way out at 6.4 astronomical units from the Sun. That sits beyond Mars, and comets don't usually start releasing gas and dust that far out. Water ice needs more heat to sublimate. The Zwicky Transient Facility joined the observation effort, spotting a small fuzzy cloud around the object stretching 3 arcseconds across. By July 2nd, with 122 observations from 31 different observatories compiled, the International Astronomical Union confirmed it. This was the third interstellar object ever detected, earning it the designation 3I. The naming tells a story. The 3I marks it as the third interstellar visitor. Atlas honors the Discovery team. The official designation C2025N1 indicates a non-periodic comet discovered in the first half of July 2025. Only 2 other objects share that interstellar prefix. The first, One-Eye, Oumuamua, showed up in 2017 looking more like an asteroid than a comet. No fuzzy cloud, no tail, just a tumbling rock. The second, 2I Borisov, in 2019, behaved like a classic comet with prominent gas emissions and a visible tail. Now, 3I Atlas arrives with characteristics that fall somewhere between its 2 predecessors. The size keeps growing. Here's where things get interesting with the size estimates. When Hubble Space Telescope observed 3I Atlas on July 21st, scientists calculated an upper limit of 3.5 miles for the nucleus diameter, with a lower bound around 1,444 feet. Those numbers suggested something relatively small, maybe less than a kilometer across. Then the Vera C. Rubin Observatory took its turn. The images from late July painted a very different picture. The data pointed to a nucleus approximately 7 miles, or 11.2 kilometers in diameter. That's a significant jump. Mass estimates climbed past 33 billion tons, far exceeding initial calculations. This upward revision in size is what people mean when they say 3I Atlas is getting bigger. The comet itself isn't actually growing. Instead, better observations with more powerful instruments reveal the true scale of what we're looking at. Early measurements relied on brightness and distance calculations that provided ballpark figures. As more telescopes joined the effort and imaging improved, the real dimensions emerged. The fuzzy cloud surrounding the nucleus, called the coma, also expanded dramatically as the comet approached the Sun. Measurements from June showed the coma at 13,040 kilometers across. By July, it had doubled to over 26,000 kilometers. Recent images capture complex tail structures stretching up to 1 degree across the sky, translating to roughly 3 million kilometers in actual length. An unmistakably interstellar orbit. The orbit of 3I Atlas confirms beyond doubt its interstellar origins. Numbers don't lie in orbital mechanics. The eccentricity value of 6.14 means this comet follows a hyperbolic path. In simpler terms, it's not bound to our Sun. Objects orbiting normally have eccentricities between 0 and 1. Anything above 1 indicates an unbound trajectory. The comet entered from the southern celestial hemisphere, moving at 58 kilometers per second relative to the Sun. That's called the hyperbolic excess velocity, the leftover speed after accounting for the Sun's gravitational influence. Its inclination of 175 degrees puts it in retrograde motion, traveling backward compared to the planet's orbital direction. Journey through the solar system. The comet reached its closest point to the Sun, called perihelion, on October 29, 2025. At that moment, it sat 1.36 astronomical units from our star inside the orbit of Mars. For reference, 1 astronomical unit equals the average distance from Earth to the Sun, about 93 million miles. The comet's speed peaked at 68.3 kilometers per second during perihelion. For that milestone, it made several close approaches to the other worlds in our solar system. On October 3rd, it passed within 0.19 astronomical units of Mars. That's roughly 18 million miles, close enough for Mars orbiters to grab detailed observations. Venus got a visit on November 3rd at 0.65 astronomical units. Earth's turn comes on December 19, 2025, when 3i Atlas reaches its closest approach at 1.8 astronomical units. That puts it about 167 million miles away, far beyond any threat to our planet. After leaving the inner solar system, the comet heads towards Jupiter, making its closest approach to the giant planet on March 16, 2026 at 0.36 astronomical units. The trajectory appears almost like a straight line when you plot it out. High eccentricity does that, making the hyperbolic curve so stretched that it looks flat across our solar system scale. Calculations suggest this comet originated from somewhere in the Milky Way's thin or thick disk. Age estimates range wildly from 800 million years to 14 billion years, depending on which models you trust. Some analyses indicate possible past encounters with 25 different stars within 1 parsec over the last 10 million years, though these remain speculative. Alien chemistry. The composition sets 3i Atlas apart from typical solar system comets. Spectroscopy breaks down the light reflecting and emitting from the coma into its component wavelengths. Each element and molecule has a unique fingerprint. Results from multiple observatories show an unusually high ratio of carbon dioxide to water, about 8:1. Most comets at this distance from the Sun should show more water activity. Carbon dioxide sublimates at colder temperatures than water ice, which explains the early activity detected at 6.4 astronomical units. The chemistry gets weirder. Scientists detected carbon monoxide, carbonyl sulfide, cyanide, and atomic nickel vapor in the coma. The nickel finding raised eyebrows. Measurements show nickel abundance 10 times higher than solar system averages, and it appears pure without accompanying iron. That combination is rare among known comets. Other carbon-bearing molecules like C2 show depletion compared to typical comets. Water remains surprisingly low for something at this distance from the Sun. One theory suggests an insulating crust formed during billions of years in interstellar space, keeping volatiles locked inside until solar heating breaks through. Another possibility involves formation in an exotic protoplanetary disk with different chemical ratios than our solar system. Webb and the Very Large Telescope weigh in. The James Webb Space Telescope added more details on August 6, 2025. Its infrared instruments detected heavy carbon-13 enrichment in the carbon dioxide molecules, along with water ice signatures. The Very Large Telescope in Chile found increasing amounts of cyanide and nickel over time as outgassing accelerated. By September, hydrogen cyanide production reached 4.5 times 10 to the 25th power molecules per second. That translates to about 2 kilograms of HCN released every second. Dust grain measurements show a mix of sizes, with 1 micrometer particles traveling at 22 meters per second and larger 100 micrometer grains moving at 2 meters per second. A fleet of observers. Multiple space missions captured views of 3i Atlas during its journey. Hubble provided that crucial July 21st image showing a teardrop-shaped coma. The Mars Reconnaissance Orbiter's HiRISE camera grabbed a full coma view from 18.6 million miles away on October 2nd. MAVEN, another Mars orbiter, imaged the hydrogen halo surrounding the nucleus. Down on the Martian surface, the Perseverance rover pointed its camera skyward on October 4th and captured a faint smudge representing the distant comet. Stereo spacecraft and SOHO Solar Observatory caught glimpses as 3i Atlas passed near the Sun between September 11th and October 2nd. Even deep space missions like Lucy and Psyche, headed to asteroids in the outer solar system, turned their instruments toward the visitor. Lucy observed from September 15th to 17th, while Psyche took its look from September 8th to 9th. Ground-based telescopes coordinated a massive observation campaign. The Very Large Telescope in Chile used polarimetry to measure light-scattering properties. The results showed high negative polarization values. Gemini South captured images of the fuzzy coma. Amateur astronomers contributed too. Michael Yeager stacked images from November 8th, revealing 5 distinct jets streaming from the nucleus. Recent posts on social media from astronomy photographers show complex tail structures. The Nordic Optical Telescope released images from November 11th, confirming the comet remains intact after perihelion. One prominent feature appears as a sunward anti-tail, a structure pointing toward the sun rather than away from it. This anti-tail stretches 200 arcseconds in length. The main tail, pointing away from the sun, extends up to 900 arcseconds. Light curve data tracking brightness over time shows a steady increase from May through August 2025. The comet peaked around magnitude 11.5 to 12, bright enough for backyard telescopes, but too dim for naked eye visibility. Some observers hoped it might brighten further, but predictions suggested it will remain a telescope target throughout its passage. No major outbursts or fragmentation events occurred, unlike some comets that break apart under solar heating stress. The artificial origin debate. The unique characteristics spark debates in the scientific community. Most astronomers favor natural explanations for everything observed. Comets are messy objects with complex behavior driven by internal structure and composition. Sunward jets raise questions because they seem to push against normal comet behavior. Typical jets point away from the sun as volatile sublimate. Sunward jets might indicate some kind of propulsion or unusual outgassing pattern. Professor Avi Loeb at Harvard suggested considering artificial origins, pointing to the anomalous jets and other characteristics. His analysis noted that non-gravitational acceleration parameter A3 equals 0, meaning the comet's path shows no deviation from pure gravitational motion. He described this as machine flat trajectory control. Critics quickly responded. Chris Lintott from Oxford and David Kipping from Columbia pushed back against artificial origin theories, arguing the evidence points to natural processes. Cosmic ray exposure over billions of years could create surface crusts that direct gas jets in unusual directions. The pure nickel without iron might result from specific formation conditions in a metal-rich protoplanetary disk. The low water and high carbon dioxide could simply mean this comet formed in a colder region of its home system than where our solar system's comets originated. SETI searches turned up no signals. Statistical analyses put the probability of extraterrestrial intelligence origins between 0.0026 and 0.3%, depending on assumptions. Those numbers suggest natural explanations deserve priority. Why we can't send a spacecraft. The impossibility of sending a spacecraft to intercept 3I Atlas adds frustration to the scientific discussion. Calculations show any mission leaving Earth would need a change in velocity of at least 24 kilometers per second just to match trajectories. Our current propulsion technology can't deliver that kind of performance with a useful science payload. Mars-based observations provided the next best option. The European Space Agency's ExoMars Trace Gas Orbiter refined trajectory calculations using Mars as a closer observation platform. Those measurements improved accuracy by a factor of 10, confirming no unexpected deviations from the predicted path. Future observation plans. Future observation plans extend through several years. The James Webb Space Telescope scheduled additional observational time in December 2025 for ultraviolet spectroscopy. Ground telescopes will continue tracking 3I Atlas through 2026 as it heads outward past Jupiter. After that, space-based observatories like Sphere-X could maintain observations until approximately 2028. By 2029, the comet will fade beyond detection limits of current instruments. The compiled data could inform future mission designs. The European Space Agency's Comet Interceptor mission might encounter another interstellar visitor if one appears with sufficient advance warning. How 3I Atlas compares to its predecessors. Comparing 3I Atlas to its predecessors reveals patterns and differences in interstellar objects. 1I Oumuamua stretched about 200 meters long, showed no coma or tail, and exhibited unusual non-gravitational acceleration that sparked artificial origin speculation. Its age estimate sits around 1 billion years. The shape remains debated, with suggestions ranging from cigar to pancake configurations. 2I Borisov measured roughly 1 kilometer across, displayed high gas and dust production similar to solar system comets, and showed chemistry resembling objects from our own Oort cloud. Age estimates place it at 1.7 billion years, Its eccentricity of 3.6 confirmed interstellar origins, but with less excess velocity than 3I Atlas. Now, 3I Atlas arrives with an eccentricity of 6.14, the highest of the three. Size estimates range from a few hundred meters to 11 kilometers depending on the measurement method. Its age potentially spans from 800 million to 14 billion years. The activity level sits between the inactive Oumuamua and the highly active Borisov. The carbon dioxide dominance and depleted water content mark it as chemically distinct from both predecessors and from typical solar system comets. These differences suggest interstellar space harbors a wide variety of planetary system debris, each reflecting the formation conditions and chemical makeup of its home star. What one comet can teach us about the galaxy. The scientific value extends beyond the object itself. Every interstellar visitor provides a sample of another planetary system delivered to our doorstep. We can analyze its composition, measure its properties, and infer details about where it formed. The high carbon dioxide suggests cold formation temperatures. The metal-rich chemistry, particularly the enriched nickel, points to a protoplanetary disk with different elemental abundances than our solar nebula. Isotope ratios, like the heavy carbon-13 and carbon dioxide molecules, reveal nuclear processes and chemical pathways active in that distant system. Age estimates, though uncertain, bracket formation time periods that might coincide with peak star formation epochs in the Milky Way's history around 3 to 11 billion years ago, sometimes called cosmic noon. The cosmic ray exposure calculations add another layer. Space between stars isn't empty. High-energy particles stream through the interstellar medium constantly. These cosmic rays chip away at surfaces, alter chemistry, and leave measurable signatures. The cosmic ray dose received by 3I Atlas implies billions of years of exposure, supporting the older age estimates. This extended journey through the galaxy represents a time span longer than life has existed on Earth in some scenarios. More visitors to come. Statistical projections estimate how many interstellar objects pass through our solar system undetected. Current detection capabilities catch only the brightest and closest visitors. Models suggest several such objects could be within Jupiter's orbit at any given time, dozens more in the outer solar system. Most pass unnoticed because they're either too small, too faint, or positioned in parts of the sky not covered by current surveys. The Atlas system and other next-generation survey telescopes increase our chances of early detection. Finding interstellar objects while they're still far from the sun gives more time to organize observation campaigns and potentially even plan intercept missions. A coma bigger than Earth. The expanded coma dimensions create spectacular visual displays even if the comet itself remains modest in size. That 26,000-kilometer diameter measured in July exceeds Earth's diameter by a factor of 2. The tail structures extending millions of kilometers showcase the scale at which cometary activity operates. Material ejected at the nucleus gets pushed by solar radiation pressure and the solar wind, creating those characteristic streamer patterns. The antitail porting sunward represents heavier particles that fall behind the nucleus in its orbit, creating an optical illusion of pointing the wrong direction when viewed from Earth. Rotation period measurements settled on values around 16 hours, suggesting a nucleus spinning once every 2/3 of a day. Color measurements show reddish hues, typical of organic-rich materials that have been irradiated over long time periods. The absolute magnitude greater than 15.4 indicates a relatively dark surface with low reflectivity, another common trait for comet nuclei and asteroids that have spent time in space. These small details build a complete picture of an object that formed in another star's planetary system billions of years ago and now passes briefly through our cosmic neighborhood. A global effort. The observation count reached 697 data points across 182 days by late 2025. This represents an unprecedented international collaboration to study a transient visitor. Professional observatories on every continent, space missions throughout the solar system, and amateur astronomers in backyard observatories all contributed pieces to the puzzle. The data will fuel scientific papers for years as researchers analyze details, test formation theories, and refine models of interstellar object populations. Farewell to an interstellar wanderer. The journey continues as 3I Atlas races away from the sun. Its velocity relative to our star ensures it will never return. Once it passes beyond Neptune's orbit, it rejoins the dark space between stars, traveling for millions or billions of years until perhaps encountering another stellar system. Future civilizations around distant stars might detect it passing through their space by the way we detected it in ours. The timeline of perihelion passage, planetary flybys, and eventual departure plays out like clockwork according to gravitational mechanics. December 19th marks Earth's closest approach, offering one final prime observation window before the comet recedes into the outer solar system depths. 3i Atlas carries evidence of processes and conditions in another corner of the galaxy. Its chemistry tells stories of disk formation, planet building, and the ejection mechanism that sent it wandering through space. The pure nickel vapor and carbon dioxide dominance provide clues that theorists will puzzle over, testing formation models and chemical evolution scenarios. Each anomaly offers a chance to refine our understanding of how planetary systems work across different stellar environments and time periods. The debates about natural versus artificial origins, while garnering public attention, represent a small sidebar to the main scientific value. Whether some voices speculate about alien technology or not, the chemical and physical evidence points overwhelmingly toward a natural interstellar comet with unusual but explainable properties. This visitor from beyond reminds us that our solar system exists within a galaxy full of similar systems, each producing debris and sending it sailing through space. The statistics suggest we should expect more interstellar objects in coming years as survey capabilities improve. Each one offers fresh insights and comparisons. Together, they build a catalog of extrasolar material that complements the distant observations of exoplanets and protoplanetary disks. We can't yet travel to other stars, but these visitors bring samples of those distant worlds to us. The fact that size estimates keep climbing as better data arrives show how much remains unknown, even about objects passing relatively close by. The 7-mile diameter figure might not be the final word. Future analysis could revise numbers again as scientists refine their techniques and incorporate additional observations. For now, 3i Atlas holds the title of largest confirmed interstellar object detected, surpassing both its predecessors and highlighting how much we're still learning about these cosmic wanderers. The Manhattan-size comparison captures imagination more effectively than astronomical units and kilometers. Imagine a chunk of ice and rock the size of a major city sailing through space at speeds that would cross continents in seconds. The coma surrounding it dwarfs Earth. The tail stretches distances that would reach from Earth to the Moon multiple times over. These scales demonstrate the majestic scope of cometary phenomena, while reminding us how small and local our perspective remains, despite all our telescopes and spacecraft. 3i Atlas will fade from view in coming years, but the data it provided enriches our understanding of the galaxy's composition and the diversity of objects orbiting distant stars. That legacy persists long after the comet itself becomes too faint to observe, joining the dark matter and undetected objects that fill the space between stars, waiting for their chance to sweep through another stellar system and tell their story once more.